Welcome, everyone. It's my absolute pleasure to bring us all to order for the 2025 Cady Lecture. The George Cady Endowed Lectureship in Chemistry was established in memory of Professor Cady by his family, friends, and colleagues in 1994, and we've been holding the lecture annually ever since. You can read a little bit about Cady's career trajectory in the program that comes along with the lecture today, but I'll just mention a few brief things. So Cady was a pioneer in fluorine chemistry, examining the properties and reactivity patterns of fluorinated compounds and developing new fluorination reactions, including the fluorination of carbon monoxide and the synthesis of trifluoromethyl hypofluorite. For all of his work in fluorine chemistry, he was a recipient of one of the very first Prix Moissan prizes, which was named after the father of fluorine chemistry, Henri Moissan. A fun fact about George Cady is that when he was born, his father, Hamilton Cady, who was also a chemist, and was in fact the chemist that discovered that helium could be extracted from natural gas, almost named George Neon for new one. So it's a real honor to have Shannon, Professor Shannon Stahl with us today as our 2025 Cady Lecturer. He's joining us from the University of Wisconsin-Madison, and I've really admired the science that he's done for a number of years in terms of its breadth, but especially its depth. He's a world-renowned leader in oxidation catalysis, whose research has really transformed our scientific understanding and the industrial practice of aerobic oxidation. His work has produced field-defining contributions across pharmaceutical synthesis, biomass valorization, plastics upcycling, and electrocatalysis. He started his academic journey getting his bachelor's degree in chemistry at the University of Illinois Urbana-Champaign. He went on to get a PhD in chemistry at Caltech with Professor John Burkaw, where he looked at developing a mechanistic understanding of alkane activation by platinum complexes. He then went on to do postdoctoral work at Massachusetts Institute of Technology, working with Professor Steve Lippard, again in deep mechanistic studies, but this time instead of with transition metal complexes, with enzymatic systems in biology. He then began as an assistant professor of chemistry at the University of Wisconsin-Madison, where he remains to this day, having held numerous distinguished professorships there over the years. His work at UW-Madison spans a wide range from catalytic oxidations with molecular oxygen, which we're going to hear a bit about today, catalytic methods for biomass conversion and valorization, electrocatalysis and electrochemical organic synthesis, as well as energy storage and conversion. There's many aspects of his science that I find intriguing, including the idea of transferring things from really disparate areas of chemistry and science to create innovative solutions in catalysis. For his work, he's received a number of awards, including being elected as a member of the National Academy of Sciences and the American Academy of Arts and Sciences. He's received the American Chemical Society Award in Organometallic Chemistry, as well as the American Chemical Society Award in Affordable Green Chemistry. He also very recently won the 2025 European Federation of Catalysis Society's Robert K. Grasselli Award for Catalysis. And today, we're adding to that accolades collection, and it's my pleasure to hand him the plaque for the 2025 Cady Lecture and hand the floor to him so you can see the booth.
Well, Brandi, thank you for that very kind introduction. Thank you also and your colleagues for this opportunity to visit. It's been a delightful visit, just wonderful science over the past couple days. And so I just want to say thank you to the faculty and students who took time out of their schedule. It's been very stimulating. So, and a lot of more connections, I just kind of alluded to in the introduction, I think what's fun about science is that each of us has unique experiences, right? And so, what really fosters innovation, I think, is kind of making these connections across disparate kind of fields where you kind of bring your own experience to bear on fields that, every one of us is unique in terms of the way we kind of bring kind of our own backgrounds to a field. And so I'm grateful to have this chance to share kind of a passion of mine. It's a little more curiosity-driven, kind of fundamental. There's definitely applied aspects. So I have a kind of just a desire to kind of have impact, in a practical domain, but a lot of it is driven by very fundamental questions. And so that's what I want to share with you today, is about this topic. And my clicker is, Brandi taught me how to do this, so I'm going to try it one more time. What does that say? Annotate. I got to click on the slide? And then now it should work? Okay, bingo. Okay. So I need Brandi to kind of follow me around to seminars so I can learn how to run my computer here. So, but the story is going to cut across a few different disciplines here as it relates to energy conversion in fuel cells and aerobic oxidation. It's really rooted in aerobic oxidation, catalysis for chemical synthesis, as I'll mention in a moment. And then the homogeneous catalysis cycle that I show here will also be then connected to heterogeneous catalysis, which I'll have a chance to touch on just briefly at the end. So I thought I'd just kind of show this little personal introduction just because it kind of shows kind of what motivates kind of the science that I did here in the ensuing kind of 50 minutes. So I did undergraduate research in a transition metal chemistry class. I was telling the students at lunch how I kind of started in chemical engineering, thinking it was more practical and I could get a job after 4 years, and then I just fell in love with organic chemistry, thanks to an individual named Pat Shapley. I don't know if any of you know her, but she was a very inspiring lecturer, and I had a chance to work in her lab. And then at summers, I worked in medicinal chemistry at Abbott Laboratories, now AbbVie, the pharmaceutical branch. And that's where I took a liking to organic synthesis, kind of building on the sophomore organic, but I fell in love with metals, and so I ended up doing organometallic chemistry, focused on methane oxidation. There's this fascinating Shilov system that I studied that takes methane selectively to methanol, so one of these holy grails. But one of the things that I note in this red box is the fact that it uses stoichiometric platinum-4 as the oxidant. So, not going to find practice in industry anytime soon. And so partly while I was in graduate school, there were so many metalloenzymes that were getting crystallized and structurally characterized in the kind of 1990s. And so it was with that motivation kind of also coupled with kind of this kind of challenge of how do you change the oxidant in the Shilov chemistry, that I thought I should learn how to use oxygen. And so I'll go study how nature does it. And so some of the story that I want to share with you kind of relates to kind of why this is not the path that I followed of methane monooxygenase, but there was just this curiosity, why, if I wanted to connect kind of what nature had done about using oxygen as an oxidant and transferring that to chemical synthesis, why do we have this oxidant? Like we teach sophomore organic, we don't teach aerobic oxidation, right? It's the world's most environmentally benign, economically viable oxidant, but we don't teach it, okay? And I think that's kind of the curiosity-driven research kind of component of this is why do we have this amazing oxidant all around us and we don't know how to use it, okay? And so that was kind of what motivated my career and at Wisconsin starting up. But obviously this has a long history, right? Oxygen on our planet, right? Billions of years old. And I think it's fascinating, right, to think about how life evolved and how oxygen was so central and it was only because of oxygen that we can have some of the more complex life forms, partly driven by the energy that we capture by having an oxygen as our electron acceptor rather than sulfate, for example, right? The driving force, you get much more energy out of using oxygen as an oxidant. And so, I think there's just kind of fascinating connections that we can make. These are some of the aerobic oxidation reactions that we don't teach about in sophomore organic, but nonetheless are kind of a framework for thinking about how O2 can be used in chemical synthesis. So there's radical chain. So industrially, this is actually one of the most important classes of aerobic oxidations. If we do teach it, it's typically in the radical chain context, although we're usually teaching radical chain halogenation as opposed to aerobic oxidation. But it's used to make the water bottle that I have up here in the front and maybe sitting with you at your benches is a plastic material that's essentially made through a selective aerobic oxidation of these benzylic methyl groups. Yesterday, I made some reference to these methane monooxygenase, or these cytochrome P450, which is conceptually related to methane monooxygenases. I'll show you in a moment. But these use this so-called reductive activation, where you use a sacrificial reductant combined with O2 to drive oxygen atom transfer. And it was really this use of this sacrificial reductant that motivated me to go away from the methane monooxygenase class of enzymes as I went into synthetic chemistry. Because if you think about this oxidase type scheme, again, inspired by oxidase is kind of a term that's used for these enzymes that are driven with O2 reduction, but don't transfer oxygen atom to the substrate. So formally, they're using the energy of O2 reduction to drive a substrate oxidation. Okay, and so that scheme looked very compelling to me as a synthetic chemist, because what it meant is I can use oxygen as an oxidant, and I can essentially couple O2 reduction to any synthetic oxidation reaction, whether it's carbon-carbon bond formation, just simple dehydrogenation, carbon-nitrogen, carbon-oxygen. In principle, I'm limited only by the catalyst that I could identify. Okay, but I want to kind of build the bridge to kind of how do we think about this beyond just these simple kind of two coupled half reactions, okay? And maybe what I wanted to kind of just share a slide. You know, the methane monooxygenase, very similar to cytochrome P450 that I had on the previous slide. The key point here is that it uses this sacrificial reductant in order to activate O2 to use a peroxide level oxidant. But it doesn't do this, and I mentioned this yesterday, this idea of doing a dioxygenase reaction. Partly that's an energetic consequence, and this was, if you were at the lecture yesterday, I mentioned this idea that if you can reduce oxygen to hydrogen peroxide or hydrogen peroxide equivalent, you essentially get an oxygen atom at the peroxide level oxidation state, which is a much more potent oxidant than even O2 itself, right? So it's almost 500 millivolts higher in redox potential than O2 itself in the 4-electron coupled mode, because this 4-electron is just the average of these two. And so you can actually get a much more greater driving force if you first reduce O2 to hydrogen peroxide. Okay, but that's obviously, as a synthetic chemist, as I mentioned, I can't afford the luxury of adding a reductant just so that I can use O2 as an oxidant. Okay, so that just, from a synthetic chemist perspective, that didn't make sense. So I'm going to be constrained, if I'm going to follow this oxidase model, the idea is that I'm going to be constrained to a driving force of 1.23 volts. Okay, so that's essentially the thermodynamic limit that I can get from O2 reduction to drive whatever substrate oxidation I have here. Now, you know, this coupled redox scheme, and I've tried to make some connections for you already, but you know, nature has these interesting lactases and other oxidases that essentially do something similar. Lactases are some of the most efficient O2 reduction enzymes, where they can even get up very close to the 1.23 volt potential, near theoretical potential of O2 reduction to drive some substrate oxidation. It makes lignin, for example, which we're now trying to, you know, go the other direction of depolymerized lignin. There are fuel cells. You know, this is, again, basically a redox coupled, so the hydrogen oxidation, I just show the protons coming through rather than coming out, because those protons are needed, essentially in a fully coupled way to make water and drive the energy production in a fuel cell. I'll try to kind of connect those dots. This is the synthetic oxidase scheme that I'll show you, and then I'll end the talk kind of talking about some heterogeneous applications that actually have some close connection to some things I talked to Dan Gamlin about this morning as it relates to kind of thinking about how a material or a particle essentially kind of couples redox reactions kind of embedded in it. You know, this is another kind of feature that we often see in synthetic aerobic oxidations, are these redox cascades. You know, the electron transport chain, I think, is a good kind of inspiration or context for thinking about what synthetic chemists have done, where you essentially use O2 as the terminal oxidant to drive some synthetically useful oxidation reaction. You know, nature's basically using this essentially for energy production. It's using its hydrogen equivalent, so that's like fuel cells, FADH2 or NADH in protons, essentially is your H2 equivalent. And then ultimately what it's doing is pumping protons to make ATP, which is our energy carrier. And so this is all about energy production, just like a fuel cell. But synthetic chemists have hijacked similar redox cascade with mediators that kind of relay the redox power of O2 to synthetic oxidation chemistry. Here's another interesting one. Part of my lecture is going to focus on this very unique redox coupled NOx So NO, nitric oxide, NO2, that turns out to be very special for reasons that I'll elaborate. A lot of what I'm going to share with you, this is kind of a framework that's going to come up numerous times, so I kind of want to orient you. What I've done is essentially created a kind of a Latimer diagram and put it on its side, because essentially what you see is kind of a step function. What you have is the theoretical potential of O2 reduction to water. Then you have hydrogen down here at 0. That's our reference potential. That's the theoretical limit of a fuel cell, 1.23 volts. But of course, we don't get that, right? And so the idea is that, one of our favorite demonstrations in Gen Chem, right, is taking a hydrogen balloon and blowing it up, right? So this is hydrogen plus oxygen. That's 1.23 volts times 4. Okay, that much energy is basically used to make just heat and light, right? And that's because you're delivering those electrons at 0 volts, because you're using hydrogen as your source of electrons. But of course, if you're running a fuel cell, you don't want electrons at the 0 volt potential of hydrogen, because then you would have nothing left over, to drive electricity, power. And so we really want to be up at 1.23 volts. The problem is if you take the hydrogen molecule, you split it out into protons, you get those at 1 molar, okay, standard state. And then you take the electrons and you put them up at 1.23 volts rather than at 0 like they are in the molecule hydrogen. You don't get anything to happen. There's not even a pop. Okay, if you light a match, you might break the balloon, but if those electrons are coming in at 1.23 volts, there's no energy given off. In fact, there's no reaction. Okay, and so in fact, in a fuel cell, if you set your cell voltage at 1.23 volts, you don't have anything happening. Okay, and the reason is you got to energize the electrons to get over kinetic barriers. Okay, and so in a real fuel cell with platinum, with the world's best catalyst for O2 reduction, you basically have to energize your electrons from 1.23 volts and make them more reducing to about 0.95 till you can finally start to get over the kinetic barrier. Okay, but if you're in a fuel cell car and you step on the gas, you need more current, you're actually going to go even lower. So you're going to basically need more driving force, and so you're going to drive this lower. So you're going to get less cell voltage, but you're going to get more current out. And so essentially you have something called an overpotential. So you're kind of wasting the energy of basically energizing the electrons. And so what you have left is just less cell voltage, okay, out of your fuel cell. So that's kind of the limit. You basically want 1.23. You're never going to get that. Practically, you can get close to 0.9 because hydrogen doesn't have a huge overpotential. So basically, you can take the same argument, flip it. You can't oxidize hydrogen, right? That's the thermodynamic limit of 0. If you want to get any net transfer, you have to apply a little overpotential. It turns out with hydrogen, because it's just spherical s orbitals, it's kinetically a lot easier to pull those apart. It's only 2 electrons. And so it turns out there's very little overpotential there. So you get, maybe close to 0.95. Now, something I'm going to talk to you about is a lot of our aerobic oxidation reactions, it turns out, are 2-electron redox cycles. And so we're actually taking O2 and reducing it to hydrogen peroxide. If you do that, turns out you're actually limited to about 700 millivolts as your maximum theoretical. So that's like the equivalent of 1.23. But if you're only going to hydrogen peroxide, you're only going to get, it's a question I often ask incoming graduate students when I'm talking about aerobic oxidation is, is oxygen a strong oxidant? Theoretically, maybe. Practically, it depends, right? It depends on how, I thought the screen was going, okay. So the question is how is oxygen being used as an oxidant, okay? And it kind of depends on the mechanism by which oxygen is being used, whether it's a strong or a weak or a moderate oxidant. Okay, so so this is fuel cells. This is not a talk necessarily about fuel cells, although it has many important connections. But let's do the same kind of analysis, but now with organic molecules. Okay, so I mentioned back here hydrogen is at 0 volts. So when you oxidize an organic molecule, and I mentioned this again, this is kind of a reference to yesterday. What you see, these are the oxidants. Okay, so that's 1.23 volts. That's hydrogen peroxide at 1.78 volts. These are other synthetic oxidants, okay? So you can see they range from ozone up at 2.08, iodine down at 0.54, so you've got a range of synthetic oxidants, okay? What I've done over here is actually put in the organic redox potentials that are based on going to the NIST, the National Institute of Standards. Basically, you can get enthalpies and entropies of formation, and so you can then use that to get a net free energy of reaction to make hydrogen, and then you can convert that into a standard potential, and that's what these values are. So the point that I want to highlight here is that, I agreed that we are not going to get access to the hydrogen peroxide potential, 1.78. So we're going to max out at 1.23. So is that going to be enough to do what we want to do? What I want to highlight here is it's more than enough to do everything on this side, right? So at least thermodynamically, we've got more than enough driving force at 1.23 volts to do all the organic chemistry oxidations that we want, including things like epoxidation. Okay, I'm not saying they're going to be accessible, but the thermodynamics are there to drive these reactions. Okay, so then the question is do we have catalysts that allow us to do that? And let's talk about what it would take to achieve that goal. So same kind of analysis that I had here for a fuel cell. If we have an oxidant of O2, 1.23 volts, and we have a substrate that no longer is at 0 because hydrogen is at 0, the substrates that I showed you on the previous slide, right, they're going to vary. It's going to depend on what reaction it is. And so that value for the substrate oxidation is going to go up and down, right? So it depends on what substrate we're oxidizing, but it's going to be somewhere kind of below 1.23 for sure. Like I mentioned that epoxidation is about 0.8 volts. So that's going to actually be pretty high, okay? But that's essentially the redox potential that I have here and the redox potential that I have here. And so in order to have success, what it means is I need my catalyst to kind of sit somewhere in the middle so we have a successful thermodynamic cascade so that O2 can oxidize my catalyst, and then my catalyst can oxidize my substrate. Okay, so that's the substrate basically sitting somewhere in the middle. And this, I'll be honest, that I spent 15 years in my career without any appreciation for this concept that I'm explaining to you. It was only after I worked in the center with Brandi on fuel cells that I started to appreciate kind of this connection that essentially our catalyst sits somewhere in between our oxidant and the substrate. Okay, and then the idea is where does that catalyst sit? And it turns out that if you want to reduce oxygen to water, it turns out that most molecular catalysts are pathetic. Okay, and so most molecular catalysts are like way down here. So they're wasting, their redox potential is typically rather low, so you waste a lot of driving force. You basically have to get your catalyst to be rather reducing before it binds oxygen and actually promotes O2 reduction. Okay, and so for the most part, we have catalysts that actually are not very strong oxidants. So this is another kind of way of answering the question, is oxygen a strong oxidant? Well, if you're going to follow this mechanism, it kind of depends on what catalyst you use, because how are you relaying the redox power of oxygen to the catalyst, which actually does the substrate oxidation, right? Because we all know, we always talk about oxygen being a ground state triplet, and so there's kind of spin barriers, and the thermodynamics for one electron reactions with O2 are pretty lousy, right? And so as a result, we don't get many good reactions directly between oxygen and organic molecules. So if we're going to relay it through a catalyst, the question is, are we relaying it through a catalyst with very low overpotential, so we have a lot of driving force left, or are we wasting most of it, and now we actually don't have a very strong oxidant? Okay, so that's kind of the question and the issue that I want to analyze. And so what I wanted to do is to kind of look back over some of the reactions that we've studied historically and put them into this framework, okay, and kind of see how well we did. Now, this is an after-the-fact analysis, okay, so this is essentially looking at reactions. We were doing palladium catalysis, some copper catalysis, and at some level, I'm just going to take a few kind of case studies where we have some insight to kind of analyze the reactions that we developed and ask, how well did we do? Like, are these good catalysts that are capturing a lot of driving force from O2, or are they poor catalysts, and what are the implications for synthetic chemistry? So here's one. This is a bi-aryl coupling. It turns out biphenyl is diatherm, so basically it's a kind of a thermal absorber. So you put it in kind of electrical kind of units to basically for heat transfer. But the idea is that this is also related to obviously all the Suzuki type kind of bi-aryl coupling. But I would say this is not synthetically interesting in the same way. It's more kind of just a very simple model reaction. But if you take palladium, it turns out if you use O2 as an oxidant, it will activate a CH bond. In fact, you'll activate 2 CH bonds and eventually get to this bis-aryl palladium-2. That species then undergoes reductive elimination to make palladium-0 and the bi-aryl product, and then O2 will regenerate the palladium-0 catalyst, okay? I think I'm not going to get into the details here. I think I spent too much time elaborating on the introduction, but there's different mechanisms by which this can happen. And so Dian Wang, who's now at Marquette University, was the one who kind of figured out that this is actually a transmetallation-based pathway where you have two parallel CH activations, okay, to make that biaryl. But the idea is that you essentially have a palladium 2,0 redox couple that makes the carbon-carbon bond. Okay, so what if instead, we're often doing this, it turns out we're often doing this in acetic acid. Why did we not make the phenyl acetate? Turns out people would love to have a new method for making phenol that doesn't rely on the radical chain oxidation of cumene and then a Hock rearrangement. Okay, so that's details unnecessary, but the point is that there is a co-product formation for the current process making phenol. People would love to have a direct process for making a CO bond. We have all the components needed to do that reaction. It seems like this should work, but it doesn't. Okay, anytime you mix these complexes together, it turns out it finds ways to make biphenyl and avoids phenyl acetate formation. Okay, what's going on? Well, let me kind of break it down a little bit. Turns out one of the first papers, well, the first paper that we published as a group back in, 2001, was actually understanding a process that Anychem, now called Eni, a chemical company, they were looking at methods for making hydrogen peroxide. Okay, and so they were just adding sacrificial substrates like hydrogen, like carbon monoxide to make CO2, like alcohols, as a means of making hydrogen peroxide. So the goal was essentially to come up with a better method to make hydrogen peroxide. We were modeling that system. They were using a ligand like this in their process, in their patents, and in publications. And we just said, how is that happening? So it turns out that palladium 0 will bind oxygen, make this side-unbound peroxide, and then it will protonate off the acetic acid that would come from this part of the cycle. So if X is acetate, you're going to make acetic acid every time you come around this side. That acetic acid can protonate off hydrogen peroxide. Now, that's important because, well, it turns out hydrogen peroxide is what they wanted. They were using biphasic conditions where they could segregate the organic catalyst, the organic ligand catalyst, into the organic phase. Hydrogen peroxide would go into the aqueous phase and they could build up hydrogen peroxide. In our case, where we're typically running just inorganic solvent, it turns out that the hydrogen peroxide just disproportionates into half an equivalent of O2. But the key point is we're going O2 to hydrogen peroxide. That has energetic implications because it says that we're only getting a maximum of 700 millivolt driving force out of O2. Okay, so let's come back here. So we went to the NIST web book, we looked up these two reactions, put all the components in and calculated the free energies. The free energies you get are about 0.5 kcals per mole. So almost ergoneutral, right? Barely a kcal per mole, not even a kcal per mole to actually eliminate hydrogen. So it's almost thermodynamically favorable to eliminate hydrogen. In this case, it's actually uphill by 15 kcals per mole. Okay, so that's much more difficult. So this is a thermodynamically more challenging reaction. Of course, you can use kind of delta G equals minus NFE to figure out what those thermodynamic potentials are, and it's about a 300 millivolt difference. Let's go back to this kind of vertical diagram. There's our 1.23 volts. But I told you, we don't actually get O2 at 1.23 volts. At best, we're getting 700 millivolts. And of course, that's going to cascade to some potential, and we don't actually know where our palladium catalyst is. What we know is if the palladium catalyst is going to successfully make phenyl acetate up here, it's going to have a potential above 320. But we don't know where our palladium catalyst is. We've just started figuring out how to actually measure those values. It's actually not trivial, and you can't actually find them in the literature for palladium 2,0 couples. But look at the benzene, okay? So we've got a driving force from here to there that's just not adequate. Presumably the kinetic barriers for doing reductive elimination of a CO bond are sufficiently challenging that you don't make phenyl acetate. So, the idea is that you don't make phenyl acetate, and we know from work from people like Melanie Sanford and Jingquan Yu that you can go up to palladium 4 and now make phenyl acetate. But what we're saying is that O2 does not take palladium 2 to palladium 4. Okay, so O2 somehow kinetically is just not accessible to oxidize that palladium 2 to palladium 4, and so we're basically stuck essentially just making biphenyl, because once you get there, boom, you make the biphenyl, and that's all you're stuck with. Okay, so because we can't access the high valent palladium, we're basically on a palladium 2,0 cycle, and that means that we're going to make biphenyl instead of phenyl acetate, and that's what we observe experimentally. Okay, I'm going to come back to this palladium story, but I got to take a little hiatus on alcohol oxidation. to describe some other kind of principles here. And I come back to this system. So I talked to you about palladium. This is Jan Bachval has implemented this scheme with benzoquinone. There's another one over here that's been used for alcohol oxidation, this type of redox cascade, that uses this very interesting NOx redox couple. This is interesting in part because there's also a catalyst system involving copper and tempo that we've developed for alcohol oxidation that in some ways looks similar, okay? And I want to talk to you about the similarities and differences as it relates to alcohol oxidation according to these two schemes. So some of you maybe have been around for this individual here, worked with Forrest and Jim Mayer back in the day, and she came and did a postdoc with me and had a major breakthrough. This copper tempo catalyst system that you see here, turns out it's incredibly practical. And you literally run the reactions in a beaker open to the air as the oxidant, where you just add your substrate and you add your catalyst, you stir for about 2 hours, and then you can basically filter through a silica plug and you have almost analytically pure aldehyde. Okay, it turns out aldehydes can be actually rather challenging to make, okay? Even in spite of what we teach in sophomore organic, you don't necessarily like to use PCC, the pyridinium chlorochromate, that this is a much better method. And one of these days, we're going to write up we actually did a JChem Ed article on the lab. That's been implemented in many institutions. One of these days, I'm going to write up a little textbook module and send it out to all the textbook authors to see if we can get some green chemistry into the textbooks rather than chromium. Mechanistically, one of the early proposals by Semmelhack, who was one of the first to discover a copper tempo system, a different one, but he proposed that copper-2 was oxidizing the hydroxyl up to the oxymonium because it was long known that these oxymonium species could oxidize alcohol. So it made sense to say, okay, well, let's just oxidize it up. Turns out that the mechanism is actually more like galactose oxidase, where you bring together two one-electron oxidants. In this case, it's a modified tyrosyl radical and copper-2 that kind of work together to do an alcohol oxidation. Essentially, you've got one electron oxidant here, one electron oxidant here working together to oxidize the alcohol, and then O2 finds a way to regenerate the two oxidized states. Mechanistically, if you follow along, what you're making is an active state that has a nitroxyl that's actually bonded to copper. Okay, it turns out we did some work with Kyle Lancaster doing X-ray absorption spectroscopy on some of these nitroxyl copper complexes. This one is not stable, as you can tell, but there are some you can make. And it turns out that they're diamagnetic, okay? And so it turns out that if you look at it, it actually looks like when you take a nitroxyl radical here and copper and bring them together, it's somewhere, you could imagine, is this a copper-3 nitroxide? Is it a copper-2 radical nitroxyl radical? Or is it a copper-1 oxymonium? Okay, it turns out, based on Kyle's spectroscopy, it looks like it's somewhere between the lower two potentials. So kind of like a copper-2 radical and a copper-1 oxymonium. So it's somewhere in between. So it kind of depends on how you draw the charge transfer in that state. Nonetheless, the main point is you're bringing together two one-electron oxidants to make a two-electron oxidant, such that you now actually get hydride transfer. It's not an H-atom transfer, okay? In spite of using a radical, you're actually doing hydride transfer. We've done radical clocks and other substrate probes and basically shown there's no evidence for any radical formation. It's basically a concerted hydride transfer. If you're an organic chemist, you've probably heard of the Oppenauer oxidation. This is a Lewis acid that takes a ketone and an alcohol and does a hydride transfer docked on a Lewis acid. It basically is an Oppenauer oxidation, but with a driving force, okay? Because if you think about an Oppenauer oxidation, it's a ketone, a carbonyl, and an alcohol doing what is almost an ergoneutral reaction, right? It's one carbonyl for another. In this case, we're actually making these into mild oxidants, so there's actually a driving force for that hydride transfer, okay? Or if you're more familiar with transition metal chemistry, you've heard of beta hydride eliminations. So you can almost think about this fragment, this copper ON, basically taking the role of a noble metal that does two electron chemistry. Okay, so you basically brought together two radicals, non-precious metal components that basically now does what a noble metal does kind of in one fell swoop as a beta hydride elimination. The main point is these are really useful reactions. Okay, it turns out that there's a lot of people using this chemistry now because it's incredibly mild. okay? And so it tolerates a lot of functional groups, including anilines. Anilines are very electron rich, often susceptible to one electron oxidations. You've got iodides present, you've got alkenes and alkynes, you've got sulfur. So it's a very mild oxidant. It's been run at 50 millimole scale. This was just done in a big Erlenmeyer, okay? So just bubbling air through it, so just air is the oxidant. With tempo as the catalyst, it turns out it's exquisitely selective for primary alcohols. So even a case where you have a secondary benzylic, it will go after the primary aliphatic. This one is basically undergoing oxidation here, and then it's cyclizing to make the lactone. So the idea is that even though you have activated alcohols, it's sterically so selective that it's going after the primary alcohol, even in the presence of these activated alcohols. Another individual, Janelle Steeves, I had a photo earlier in an earlier slide of her, but essentially show that you can take this sterically less hindered nitroxyl, and now when you take away those steric constraints, essentially all alcohols work at about the same rate. Notice this is 10 minutes in solution with 1 mole % abno and copper, okay, and this is at room temperature. Okay, so this is really mild, and essentially what's happening is that the steric constraints around the tempo facilitate this mechanism, and now it turns out that you don't have the steric constraints, so it's actually very, very mild. I mean, these barriers of 10 kcals per mole, I mean, this is essentially not the turnover limiting step. Now you're limited just in the reoxidation of copper because this step is so fast, okay? And so this is and just another slide basically showing that you've got even tertiary amines, that you have in your substrate indoles. These are electron-rich molecules that are very oxidatively sensitive. But because you're bringing together two very mild one-electron oxidants, they work together in a way that essentially allows you very functional group compatible chemistry. And the fun of this is, like because it tolerates amines, you can do fun things like make an amide bond from an alcohol and an amine. Okay, and so I don't expect you to see all the structural details behind here, but there's just a lot of interesting structures, including pharmaceutical adducts, that basically allow you to tolerate. So it's not oxidizing amines, even though they're more electron rich, because it's so exquisite. It's taken advantage of the greater acidity of an alcohol to activate an alcohol, even in the presence of an amine. Okay, so even if the amine binds, the hydride transfer is slower than from an alkoxide, which is now activated to deliver the hydride transfer. Okay, and this is, again, the practicality of this chemistry has allowed it to be scaled, and so we've had several projects with pharmaceutical companies basically to scale this type of chemistry. Okay, so I want to shift, so that's this copper tempo, okay? So UW kind of originated, with Jessica's work, and I want to show you a different one, right? So this one now uses a different redox cascade. It's not using two one-electron oxidants, it's actually using this NOx redox couple. Turns out this is also practical, okay? So it turns out that Lilly has scaled chemistry like this to carry out alcohol oxidations, but they're different. And so Artavaz, what he did is he basically said, okay, we've got these two catalyst systems, and this, by the way, this NOx, we didn't originate with us. We adapted it and kind of came up with a modified catalyst system. But the point is, we wanted to understand what's the difference between a copper nitroxyl and a nitroxyl NOx, okay, co-catalyst system. And so what he did was, because the nitroxyl NOx goes through this oxymonium, he decided to basically replace this with an electrode to do the alcohol oxidation, and then basically use an electrode to drive the copper tempo. Okay, so one of these, just to kind of remind you, is going through this 1 electron, 1 proton cycle. The other one is basically going through the 2 proton, or the 2 electron, 1 proton cycle. Okay, so two different states of nitroxyl. And what you see here are these electrocatalytic waves associated with these two electrocatalytic alcohol oxidation reactions. And the point I want to highlight is notice the difference. There's about a half a volt lower potential for the copper tempo system. What does that mean? Basically, it's a half a volt weaker oxidant when you work with copper tempo. And yet, when you determine the actual turnover frequencies, you find that copper tempo is operating about a factor of 5 faster, even though it's a half a volt weaker oxidant. Okay, so the way to think about this is catalysis, right? So it's basically somehow, and I call it engineered, but it's really a discovery, basically goes through a transition state that has very low kinetic barriers. Okay, so that even though it has much less driving force, it actually operates even faster than the oxymonium. Okay, one more piece that I want to bring in from this individual, James Gherkin, who studied the nitroxyl system. So I want to, again, this is this NOx system. So this is kind of atmospheric chemists, kind of care about things like this, and there's actually, NOx chemistry is all over the, the biosphere everywhere, right? So, but nitric oxide reacts thermodynamically favorable to make nitrogen dioxide with O2. Okay, like you'd be hard pressed to find a transition metal complex that basically splits O2 cleanly with 4 electrons. Okay, like this is what this simple nitric oxide is doing. It's actually a miracle to me how a small molecule like nitric oxide splits O2 efficiently to make nitrogen dioxide. People have tried to make, porphyrins and all kinds of other complexes to split oxygen. It not only splits oxygen into the dioxo, okay, nitrogen dioxide, basically converting O2 into 2 new oxo groups, but it does so at a potential that's better than platinum, okay, for reducing oxygen. Right, this is 1.09 volts, so that you take the average of these for going from nitrogen dioxide to nitrous acid, then you do the other proton coupled electron. So this net reaction, 1.05 volts, basically the average of these two values. So 1.05 volt potential for taking O2 to water. Okay, that is absolutely remarkable to me. And obviously this is kind of known in certain spheres, but I think putting it in this context, I think is really quite striking, especially when you consider. So even under the conditions where we added tempo, we measured the actual potential. We know the hydrogen potential under the conditions at which we were conducting the reaction. So we can determine that the overpotential for O2 reduction is actually only 0.3 volts. It's actually better than platinum, even though we've introduced an extra redox cascade with tempo into this system. Okay, so to me, that's just absolutely remarkable. Now, you're never going to make a fuel cell, just to be clear. Even though it's doing better than platinum thermodynamically, we're not going to build a fuel cell out of this because you've got a gas phase catalyst. Okay, so the gas phase catalyst would just disappear the moment you start flushing oxygen through. So you can't really use it how you might want to use it. But it has implications for chemical synthesis, right? Because essentially what we're saying, let me kind of bring this back to this energetic analysis. Look at the copper-nitroxyl system, okay? So we know we're using O2, so we're going to start at 1.23 volts. We know we have alcohol oxidation, so I'll just put it, alcohols can vary from 100 to 300 millivolts, and so I'll just put some arbitrary value down here, okay? And we'll keep that fixed. So 1.23, alcohol, alcohol, so those are going to stay the same. But let's look at where those catalysts fit, okay? What I said is that there is a half a volt difference between tempo oxymonium and copper tempo. Okay, so what we know is that there is a half a volt gap between wherever oxymonium sits and wherever copper tempo sits. Okay, so what it basically says is that copper tempo is wasting a lot of the driving force from O2 reduction and sitting right down here, while tempo oxymonium actually captures that driving force quite well. Now the irony is that when it comes to alcohol oxidation, there are reasons why I like copper tempo better. Okay, because it's the better catalyst. Okay. In fact, it's because it wastes a lot of the thermodynamic driving force of O2 that it is a better catalyst, because it's now incredibly functional group tolerant. Okay, so if you're an organic chemist, you're fine wasting that driving force. You get to use the green oxidant, but you also get the functional group compatibility out of a kinetically efficient, low potential oxidant. Okay, so that's kind of the irony. It's not all about kind of, I think the title of my seminar was kind of maximizing, I forget what it was, but, the energetic efficiency of O2, but the idea of maximizing the potential of O2 in synthetic oxidation chemistry, I think it's something like that. But the whole point is, you may not want to maximize minimize the overpotential or maximize the driving force, because that may be bad if you're a synthetic organic chemist. We've actually got several other cases, I don't have time to tell you about the other ones, that we've analyzed in a similar way, which basically shows that sometimes you actually want to waste the driving force from O2 to get chemoselectivity in organic chemistry. Okay, but then there's other cases, like the one shown here, where actually the fact that we waste so much, in this case by going to hydrogen peroxide, that we've actually hindered our ability to make phenylacetate, which raised the question, why not use NOx? Maybe it could actually help us, okay, in this context. And so Sue Zoltansky actually did just that. She added NOx to this phenylacetate, acetic acid, benzene solution, and actually made phenylacetate with over 100 turnovers Why? Because we now have NOx. What is NOx doing? It's basically intercepting the palladium-2 before it undergoes transmetallation to make biaryl, and actually intercepts it and makes a high-valent palladium that now can do CO bond formation, turning on a high-valent palladium catalyzed pathway. So let me just give you a few details underneath this that I think are really important to note. O2 deprotonated, basically hydroperoxyl radical, that one electron couple, notice the potential for that. So this is why O2, so yes, there's a triplet, kind of, we say there's like a, kind of singlet triplet barrier, but what does that mean? What it really means is that when you take oxygen and try to use it as an oxidant and it goes through one electron pathways, the problem is you don't even have an oxidant here, right? So I mean, this is actually below the proton H2 potential, and so it's at a negative 0.05 volts, okay, for the one electron redox wave. So, how does oxygen react with a metal? It basically docks and makes a superoxide. So you're essentially making an adduct of this one electron adduct to make a palladium-3 superoxide if you wanted to use it with palladium. Look what NOx does. It's got 1.09 volts, so it's over a volt more stronger oxidant to do that one electron docking, okay, essentially as a nitro group, basically the nitrite, the palladium-3 nitrite, which then can undergo further oxidation at 1 volt, okay? So yeah, maybe if we could make that, we would have enough driving force to go up. The problem is we don't have enough potential to even make it, okay? And this is the problem with oxygen, is that initial one electron activation is terrible, okay? So that's why most transition metal, molecular catalysts, actually have to go down very reducing before you actually even activate oxygen, okay? Because they essentially have to go through this kind of one electron adduct, superoxide adduct formation, okay? And so by using this NOx redox couple, we can now access this high valent palladium to do the turnover. Okay, so that's essentially the story that I wanted. There's additional examples, but I think these are just kind of illustrations of how kind of thinking about the energetic consequences of using O2 as an oxidant, especially in these redox cascades, that if you introduce this NOx, we've been able to access high valent palladium chemistry. We can make oxymonium, this high potential. This is a half a volt higher than the copper tempo. And, but I also told you, we don't really want to use NOx, okay? Even my synthetic chemists, the moment they run a project with nitric oxide, they hate it. They say never again. That's what James has told me, so I've had to kind of say, what can we do that would be different? Is there a way to kind of like think differently about capturing the driving force from O2? Okay, so that's basically kind of the question that we're left with. Is how do we capture the driving force of O2 if we don't want to use NOx? So it's fine in some cases. In fact, it can even be practical. As I mentioned, Lilly has actually scaled a reaction using a tempo NOx kind of redox couple. But we'd like an alternative. So I'm just going to end this. This is more of a teaser than a thorough study. This is a project that is growing in the group, and I expect several kind of new things to be coming out in the next year or two. But we've been getting more and more interested in these catalysts that have these kind of metals and nitrogen-doped carbon. There's kind of a craze in the heterogeneous catalysis field about single atom catalysts. These are among the classes of single atom catalysts. They essentially were developed out of the fuel cell field, basically to come up with an alternative to platinum, because the fuel cell field would like to get rid of platinum and use a non-precious metal. Turns out these are the ones that have received probably the largest investment, kind of as a replacement for platinum, and they're very good oxygen reduction electrocatalysts. So if they're good oxygen reduction electrocatalysts, basically receiving electrons from an electrode and protons through a membrane in a fuel cell, we reason why can't they get their electrons and protons from a chemical bond, right? So the idea is let's use them as catalysts for substrate oxidation using O2. So that's basically kind of the simplified version of why we're motivated to understand these catalysts, because they might be able to they're not quite as good as platinum in terms of their onset potentials, but they're doing awfully well and certainly better than the vast majority of molecular catalysts, okay, NOx notwithstanding. Okay, so what are these things? These things are kind of it's a tough field, I'll be honest, kind of getting into this, because it's not these well-defined molecules that we can crystallize. And so you make these through pyrolysis. of some carbon source. This is how well defined the field is. Some carbon source, some metal source, and some nitrogen source. Okay, put it in a tube furnace, heat it up to 850 degrees, and you get materials. Okay, and there's a lot of effort to try to, like, refine the recipes. Okay, no, well, you can call them recipes to kind of make it not sound too well defined. But the idea is that that's how many of these things are made. And you can put these things in. In fact, one of the best kind of metal nitrogen carbon precursors that you add metals to is actually MOFs. So ZIF-8 actually is one of the. You got all these imidazolates, and you got zinc to kind of template sites. And so the idea is that you can basically pyrolyze a MOF that's been crystallized and well defined, and now you cook it, and basically you get this carbonaceous material that turns out to be a good template for these catalysts. So we started with this simple hypothesis. Well, let's see how well they do in oxidizing tempo to oxymonium. Because if they're any good, they ought to be able to do this. It turns out there aren't many catalysts that actually can make oxymonium with O2. Okay, because again, tempo is a pretty high potential molecule, and actually getting a molecule that actually oxidizes it, the only way it's done right now is with NOx. Okay, and that's because it's sitting at 1.05 volts, so it's got a strong driving force to oxidize, and so it can actually get to tempo, to the oxymonium. It's a little busy, so let me just kind of focus your attention over here. What I've done on the x-axis is a Poor diagram, of course, but basically what you're looking is pH on the x-axis. Potentially, you're probably too small to see. What I just want to highlight is this kind of region in gray, okay, because that's the region where the oxymonium exists. So the oxymonium exists basically above this line here. So this is the oxymonium species, and it's only above this line that exists. Otherwise, you're at nitroxyl, hydroxylamine, or hydroxylammonium, because this gets protonated as you cross this line here. And so details, not so important, but let's just say we've got to get to a high potential, and NOx is up here. Okay, it's actually better than platinum. And the iron NC is basically sitting right on that line. So it wasn't obvious that these catalysts are going to work, okay? Because at least in the electrochemical oxygen reduction reactions, they basically turn on right about the potential where you go from oxymonium, the hydroxylammonium to the oxoammonium, so to make that species. However, when we did the reaction, now we're starting with this hydroxylammonium, it turns out that this is the only, to my knowledge, if you know of another, I'd like to know it, because I'd like to buy them rather than make them. But there's one commercial source. It's actually out of Los Alamos, or actually outside of Los Alamos, but basically there's researchers at Los Alamos that basically spun out a company called pajarito powder. Okay, and it turns out to be one of the catalysts that you can buy. It's made for fuel cell industry, but we bought it and used it as a catalyst. And it turns out that it actually oxidizes hydroxylammonium under acidic conditions to the oxymonium in ways that not even platinum can do. Okay, so it actually has appealing features that even platinum is not capable of reproducing. So these are catalysts that actually can make the oxymonium. So that's kind of insight number one, is that these catalysts actually work, okay, for aerobic oxidation. So essentially, to my knowledge, it's the only non-NOx-based method to do aerobic oxidation of tempo. We're doing some other things. I thought I would just show the organic chemist this one, because it's kind of an interesting reaction. You basically take a hydrazone. You can make these diazo compounds. Some of you may know Hugh Davies, and he does a lot of these CH insertion or cyclopropanation reactions. Turned out we just made a bunch of these M-N-Cs. We also tried platinum and ruthenium. We also used our commercially available pajarito powder. Boom, you can see, almost quantitative yields kind of coming out of the pajarito powder to make this diazo compound. To do CH insertions, you can do things like, make a bunch of these diazo compounds. You can see almost, many of these, some of these you have to add a little base. So DBU is a base that basically facilitates that proton-coupled oxidation of these materials to make the diazo. But almost all of these are going in net in about quantitative yield. And that, you can do things like an enantioselective insertion. This is Hugh Davies' chemistry. So the organic chemists, can do something useful with these kind of diazo compounds that you make through this method. But you got a heterogeneous catalyst, so you can actually put them in flow and actually drop them right into your rhodium catalyzed reaction, starting from a ketone and a hydrazine. Okay, and so you basically make the hydrazone, you do the aerobic oxidation, and then run that through into this chemistry. So that's the kind of thing that we're starting to think about is, what are some other interesting aerobic oxidation reactions with these catalysts that basically are getting protons and electrons from a substrate, right, rather than an electrode and through a membrane. And then finally, can we start to get better and more sophisticated at making these catalysts? And so I have I had a postdoc, Jason Bates, who's now at the University of Virginia in his independent career, but he essentially, recognized, what we think we're doing is we think when we pyrolyze these MOFs, we basically have a bunch of zinc templated kind of N4 sites. You can think about them like porphyrins. Well, if you think about them like porphyrins, why can't we apply porphyrin-like chemistry? So can we, for example, metallate these sites directly in the same way you would metallate a porphyrin? And the conditions would be like in DMF, refluxing DMF in the presence of iron chloride. But if you got zinc present, you're going to have to get the zinc out. So he actually came up with a method to do this, where he basically was flowing kind of dry HCl N2 through. Actually, it wasn't dry. It was wet, but it was anaerobic. So you're basically flowing a nitrogen stream of HCl through this pyrolytic kind of tube furnace. And what you get out the end, basically, the zinc chloride essentially deposits because it becomes vapor phase above, I forget what the boiling point is, maybe around 750 degrees. So you basically lose the zinc chloride. And so what you're left with is a demetallited material. So you're essentially using the HCl to pull the zinc out and replace it with protons. So that's essentially what you're doing here. And then you metallate. Turns out, so you do all kinds of characterization. So we collaborated with Dave Cullen at Oak Ridge, basically to do the high resolution TEM. You can do Mossbauer. You can see this signal, this so-called D1 signal, is essentially the one that we're looking for. That's been attributed to the source of O2 reduction catalysis. We can see that. You see the eels data, basically consistent with the iron integration into the material. And then, the kind of proof in the pudding is you can determine the total iron. And from the total iron, you can get the normalized rate on a per iron basis. The problem is, many times when you metallate these things, you get iron oxide, iron metal kind of deposited. So you get various forms of iron into the system. What you really want are the single site catalysts. And so the activity on a per total iron basis actually is best out of this kind of new transmetallation protocol that we're getting. And so this is now the basis for a lot of our metallation of our new iron NC materials and MNC materials, because you're not stuck just with iron. And you can see that beats even kind of this commercially available pajarito material on this kind of per iron basis. So that's kind of one of the directions that we're going in making these materials. But I think I'm going to end there basically just to kind of bring this full circle. It was motivated by kind of understanding aerobic oxidation, thinking about how to bring these two half reactions together. But then as we started learning more about energy efficiency, we realized, hey, there's a connection here between kind of thinking about synthetic chemistry and how we're using O2 as an oxidant. And that's kind of motivated us to kind of go after these heterogeneous catalysts that do a better job of O2 reduction in a fuel cell, but maybe could be good for aerobic oxidation catalysis, kind of in chemical synthesis. So anyway, that's the kind of connection. And obviously, this has been a result of a lot of people, because you saw that talk to you about the very first paper we published. So this is a 25-year story that continues to evolve, going back to the very early days, first postdocs, some of the earliest graduate students, and then the copper-nitroxyl. There's Jessica and the team that kind of did all this kind of copper-nitroxyl work and the tempo NOx. James Gherkin is a staff scientist now. He kind of came in during the kind of solar fuels kind of area, kind of learned electrochemistry and kind of started adapting it for various applications. So he's been a real gem in the lab. And then kind of this new team that's now growing basically to go after these heterogeneous catalysts. And then obviously, grateful for all the funding that has been present over the years and we hope going into the future. But also grateful to the industrial partners that kind of are starting to look at some of this chemistry. So with that, let me thank you again for your attention.
Awesome. That was a beautiful talk. Quite a tour de force over 20 years of